Hello, my name is Vipin Kumar. I'm a professor of computer science at the University of Minnesota. And this talk is going to be an overview of a new paradigm in machine learning, which is guided by scientific knowledge. And it's increasingly becoming popular and effective for use in scientific applications, and particularly relevant for the AI Climate Institute that we have funded by NSF and NIFA. So just a little bit of a background. There's a huge interest in harnessing the data revolution that we are all living through for scientific discovery. And this data revolution has been actually in progress for last many decades. It's driven by advances in three different directions. One of them is availability of increasing amount of data. Second is the larger and larger more and more powerful computing systems, and then tremendous advances in our ability to analyze large data sets, and again, that are enabled both by the algorithms and available data, but also by the advances that have happened in machine learning, broadly speaking, over the last 5 decades. Now, these advances, of course, have been happening, as I said, for the last 5 decades, but they've accelerated in the last 10 years or so, which is what has created a huge amount of interest in application of these methodologies for scientific discovery paradigm. And as you see sort of here in these graphics at the bottom of the slide, you see the cover pages of Nature and Science, some of the most prestigious journals in the field. And I like to remind people that these actually are from more than 10 years ago. That means even about a decade ago, there was a huge interest. But given the advances we are seeing in machine learning, there's a tremendous amount of interest in using this technology for accelerating scientific discovery. So despite the fact that over the last 5 to 10 years, there has been a huge interest in scientific community for using these advances in various fields, there are some major limitations of the standard black box machine learning algorithms if you apply them straight away for scientific discovery. One of them is that they require a lot of data. Some of the biggest successes that you have seen, for example, in the form of self-driving cars, or the ability for ChatGPT to sort of have a conversation with you that looks like that's human-like. But all of these applications are driven by massive amount of data. And generally in scientific domains, the amount of data is of course increasing, but we don't have the kind of data that can be used to train these machine learning algorithms, especially the state-of-the-art algorithms that are very large in terms of number of parameters they have. The second thing is, no matter how powerful these methods are, the machine learning methods are, they often generate physically inconsistent results. And you see example of that in when you interact with things like ChatGPT, who could actually hallucinate, who could create information for you which actually doesn't exist and could be completely wrong. And as a result, of course, it sort of creates a sort of a inconsistent experience for you when you're dealing with ChatGPT. But in case of scientific problems, producing inconsistent results means that it just won't be acceptable for use in traditional scientific applications. And the third biggest limitation of black box machine learning is that it can only find, no matter how complex these methods are and how large data set they use for training, they are unable to generalize to scenarios that have never been seen or that are never present in the data. So this ability to generalize, which is so critical in the scientific domain, is missing from these machine learning algorithms that are so successful otherwise in many different ways. And as a result, when you apply the scientific machine learning algorithm to scientific problem, you often have major failures. And one of them, of course, is this parable of Google flu, which sort of a technology that Google developed about 12 years ago to be able to predict the outbreak of flu just by looking at the searches several weeks before CDC would be able to do it. And when they built this method and they put it into action, and about a year later, it started over-predicting and under-predicting in different scenarios. A similar thing happened with one of these large language models developed by Meta, which literally, which was meant for scientific field, and it only survived a few days before people figured out it's really not very good. So these are all of the major limitations of how you would sort of use black box machine learning for scientific discovery. There's another aspect that you have to keep in mind. That is, many decisions involving physical and environmental systems impact life, in fact, well-being of population and the broader ecosystem. And consequences of missing, for example, a flood warning can be far worse than an incorrect recommendation for a product or incorrect summary produced by a program like ChatGPT. So all of these sort of dampen our enthusiasm for using the state-of-the-art machine learning algorithm for scientific discovery. So if you look at these two different paradigms, one of them is a traditional paradigm that is used by the scientific community, which is driven largely by models that are built based on the first principle-based theories. They make use of some data, but not to the extent that could be made. So that's one paradigm, and that paradigm, of course, is used very extensively by the scientific community, but it has limitations because our ability to model the scientific phenomena is limited oftentimes by our understanding and also by our ability to formulate those the theories into computational models, and the inability of these models to make effective use of observations that are becoming more and more frequent in all areas of sciences. So this is one area which has promise. People have been using it for decades and centuries, but it's limited, and which is why people have started to look at the machine learning approaches. Then there are this traditional data science model that have become immensely effective, powerful in the last several decades, but certainly in the last decade or so, and especially more so in the last 5 or 6 years. But the biggest problem with these models is that they require a very large amount of data, and they fail to generalize when data is not representative. So there are two different paradigms. They both use incomplete sources of information about two key components of scientific discovery, which is theory and data. And this talk is about a new paradigm, which is a new generation of machine learning algorithms that are guided by scientific knowledge. And the core philosophy of this methodology is that it sort of sits in the spectrum that we have here, using scientific theory and using data. That is, it's meant to utilize both of them simultaneously. There's, unlike scientific theory-based model, the KGML methodology is able to make effective use of both data and knowledge. And again, unlike the data science model, which ignored the scientific theories, it's able to use the scientific knowledge to produce results that are consistent and are able to generalize beyond scenarios that have been present in the data. Now, this methodology, of course, has been evolving in our own group. Earliest paper we wrote was in 2014, almost a decade ago. And the paradigm is becoming more and more developed and more and more effective. And generally, this general area is also referred to as physics-guided machine learning, physics-informed machine learning, physics-aware AI. In all of these works, physics often should be more generally interpreted as scientific knowledge. Now, this is just to sort of remind people that KGML, even though it's a very recent field, it's a very rapidly growing community. There are a large number of workshops that are being held on this topic. We just held one in the AAAI, the main AI conference, was held in Vancouver, a program called Bridge to AI. There is a workshop on synergy of machine learning and physical sciences. There are workshops at the NEURIS conference. There is a survey produced by our group in 2021, which covered already more than 300 papers published in the field, and all of them were published in just past few years between 2017 and 2021. And there are calls or workshops and reports from DOE, NSF, and DARPA, and many other agencies. A first comprehensive book on KGML was just published in 2022 that you sort of see here on the bottom left of the screen. I was asked to organize a workshop at NSF headquarters last year, which was focused on AI-enabled scientific evaluation. And the basic premise of that workshop was that much of the advances in AI and machine learning have been driven by a small number of disciplines, for example, computer vision and language modeling. And the workshop was meant to explore the opportunities that the focus on scientific disciplines would bring to machine learning and vice versa. So the idea is that AI could revolutionize scientific discovery, and in turn, AI could really revolutionize itself by bringing in new methodologies. And KGML is literally a key component of this revolution. So this slide is meant to just give you some of the challenges that exist in modeling scientific systems, environmental systems especially, and the opportunities that are exploited by this KGML paradigm to address those challenges. So on the left, you sort of see challenges, which is one, as I mentioned earlier, is data sparsity. That is, the observation data can be used, that can be used for training machine learning models, is usually limited. It's not of the scale that you see in being able to model all the text on the internet or all the images that are available in different places, which are massive. And here we have to deal with data that's somewhat limited in scope and yet learn from them. So the sparsity of data and how do you learn from that effectively, and while using the latest advances in machine learning, is a major challenge. The second thing, which is extremely important and relates to every single problem that we deal with in the environmental sciences, and especially in the context of AI climate, is the notion of heterogeneity in space and time. That is, relationships that we are trying to build models for or make predictions for can change dramatically from one region to the other, from one farm to the other, from one country to the other, from one ecosystem to the other, which means if your data is not representative, your predictions will not generalize, and it's nearly impossible to get the kinds of data that we need for all types of heterogeneity that exist in space and time. So this is a major challenge. And the third thing, which is extremely important in nearly all of the scientific problems, is that in the scientific phenomena often involve a whole bunch of processes that are evolving and interacting over different spatial and temporal scale. For example, if I'm trying to model the greenhouse gas emission from an agricultural farm, there are multiple processes that are happening. There's a water cycle. There is a carbon cycle, which is sort of trying to do a photosynthesis using the energy from the sun and the nutrient from the soil. There are different kind of processes, the nutrients processes that are all happening and interacting at different scales. And a traditional methodology in machine learning basically treats all of this phenomena as a black box. It feeds in the data and then tries to make prediction, and with little control or little understanding or little leveraging of the fact that these processes that you're trying to model actually are happening at different scales in both space and time. And of course, lastly, the biggest challenge is that even if you manage to get high prediction accuracy on your samples and you analyze the quality of it using cross-validation methodologies, you actually are not sure whether the method is going to work in real life in situations. So one needs to be able to understand the methodology and one needs to understand the framework before you can trust it and deploy it in real life. So all of these challenges actually are addressed using this KGML paradigm, especially, for example, by bringing in the loss function, and making it guided by scientific knowledge. You can make it go beyond simply looking at the prediction accuracy. You could sort of make sure that the model that you're trying to build is able to create predictions that not only match the observations that you're trying to make predictions for, but you are also trying to conserve some of the relationships and properties that you're expecting to see in a physical system. For example, conservation of energy, conservation of mass, and things like that. And once you bring them into loss function, your entire energy landscape or the loss function landscape changes as a result. And then when you find a good solution in the landscape, you see the picture on the right side, you're actually conserving those relationships. The second thing is that even though the data may be very limited in the scientific domain, but you also have data, synthetic data from imperfect mechanistic models. These are the pure physics-driven model or the scientific theory-driven models that are traditional models, and they have a lot of imperfections, and we'll talk about them a little bit more in a bit. But even those imperfect mechanistic models can generate a lot of synthetic data, and they can be used very effectively to pre-train machine learning models that are not, of course, going to be very good, but they get trained enough that they can then are ready to make very small, they can be made to work with very small amount of observations. And you see that in the picture on the right side, where what you're seeing here is that using imperfect models, even using imperfect models, you can create imperfect scientific models. You can create enough data that can take you to the right portions of the loss function energy landscape, as opposed to the poor minima. It could sort of get you to the better minima. And the third thing is that the machine learning architectures, of course, the traditional ones, tend to be agnostic to the underlying structure of the phenomena. They are often called black box, often called knowledge free. But the KGML methodology allows you to design these architectures in ways that they can reflect the relationship among different variables and processes. Their scales and their interactions can be explicitly modeled, and there are many, many different ways of doing it that are being explored by different researchers, including our group, which basically allow us to address the ability to model complex processes, and ability to handle heterogeneity, and then, of course, work with limited data. And again, this thing, of course, can be expanded further into more complex hybrid KGML models, where if you have large-scale process-based models, that there are pieces that work very well and there are pieces that don't work very well, then machine learning components can be brought in only for those portions where the process-based models don't work very well. So there are all many, many different ways of bringing these two methodologies together. Okay? And what I plan to do in the rest of this presentation is to give you a sense of how some of these things actually can be done or are being done in this KGML framework in the context of environmental problems, and how this momentum that we have built in the last decade or so is ready to contribute to meet the mission of the AI climate, which is to basically measure, being able to model effectively the greenhouse gases that are emitted from the agriculture, and decide on figure out the management practices that could minimize that greenhouse gas emission. And this is very relevant. This is extremely important in the context of some of the biggest challenges we are facing today, or many of them arising from climate change, which is, of course, happening because of the human-induced greenhouse gas emissions, but also because of the increasing population and our need to feed this growing population without destroying the planet, because agriculture happens to be one of the biggest sources of greenhouse gases. Globally, it's about 25% of the carbon budget is due to greenhouse gases. And it turns out that if we are able to change the management practices appropriately, we can dramatically reduce this emission, and we could even turn agriculture from emitter of greenhouse gases into a net absorber of greenhouse gases. And all of this involves being able to figure out what are the right ways of doing the farming, what are the right management practices, what do you plant, where do you crop, how much fertilizers you use, how much water you put in, and what are the right environment for planting different crops, and what are the different ways of doing different types of farming, and then incentivizing farmers to be able to adopt those practices. And all of that is possible only if we can do a credible job of measuring the emission from agriculture at different locations, different regions, different farms around the country, around the world. And because of the high amount of heterogeneity that exists from one farm to the other, from one region to the other, from one ecoregion to the other ecoregion, and one management practice to the other, this is a very important but very difficult problem as well. And being able to solve this problem using traditional scientific methodology is not very effective. It's not able to give good results, whereas traditional machine learning methods have all of the problems we talked about. That is, they can work very well for locations we have a lot of data, but they don't really work well. Otherwise, they don't generalize in scenarios not seen. And this methodology of knowledge-guided machine learning is being built and developed to address this problem. So before I describe that opportunity of using KGML methodology for modeling in environmental systems, I'd like to give you this caricature here. This is sort of an abstract representation of an environmental system. I'm showing here on the right of this slide. And here the objective is to be able to see how the temperature in this lake, or the temperature in the column of the lake, is changing over a period of time in response to the weather and, of course, the season. And why is that important? Because the temperature of the lake is a master variable. It determines the quality of water, what fish can survive in this, and whether the water is safe for drinking or not. And USGS, for example, is responsible for monitoring hundreds of thousands of these lakes around the country and their health. And of course, you do that using process-based model like GLM, but they have lots of parameters, as you will see in a minute, and these parameters have to be calibrated, and calibration data for those systems are available only in very, very few places. And here you see a much more complex system in which you're sort of seeing a watershed, or you can sort of see a large region of a landscape, which is impacted by weather, the rain, the temperature, moisture, wind speed, and such. What vegetation exists on it? Is it, are there forests on the land? Is it being used for farming? And then in response to the weather and what you are what you have in the system, you may be interested in modeling a number of things. For example, you may be interested in figuring out whether the rain is going to result into some sort of a flood in the river, or you may be interested in figuring out the amount of carbon that's going to be absorbed by the crops or emitted by the agricultural system as a result of the different weather and different management practices. So in all of these cases, what you have is an environmental system that you're trying to model. The output of the system is something that you're interested in, like the emission of greenhouse gases, or a stream flow in the river, which would reflect floods or drought situations, or it could be a lake in which you're trying to figure out the quality of the water. Now, this response of this environmental system is determined by two major things. One of them is the environment, which is the weather, which I'm reflecting as X, which is the weather over a period of time. The weather drives all of the environmental systems. And at the bottom, what you see is the S, the vector S, which is a set of characteristics, the hidden parameters of the system, which in this case could be the crops that you're trying to grow in this field, or the characteristics of the soil, or the management practices of different kinds. And basically, your goal is to figure out your target value of interest given the weather and, of course, the inherent characteristic of the system. And if you could do a really good job of this, you can solve a whole bunch of problems. You can, for example, you could figure out by using this modeling methodologies as to what happens to, like, for example, what is the impact of different management practices under different weather scenarios on the production of food, the quality of food, the amount of food, and the amount of impact it has on the greenhouse gases in terms of being the emission and in terms of absorption in the soil. So this is sort of a ultimate problem that scientists try to solve in many of these areas. There is and this is called forward modeling, and there is a counterpart of this forward modeling is called inverse modeling, in which you are sort of given the input parameters like the weather. You also happen to know what's what the response of the system is, and you're trying to infer the hidden characteristics of the system. So these are the forward modeling and inverse modeling are both paradigms that are used. Much of the machine learning research has been applied in the scientific communities in the context of forward modeling. And in our research, and I'll briefly mention at different places, it's the combination of both of these forward modeling and inverse modeling being done in the context of knowledge-guided machine learning is what sort of brings us a lot of power and being able, our ability to address many of the challenges that I mentioned earlier. So now, with this background, I can go a little bit deeper into what these limitations potentially are of the process-based model and how machine learning may or may not be able to help, and how KGML, the knowledge-guided machine learning methodology, has the potential to address actually all of these different concerns. So one of the biggest issue with process-based models is that when you take a system and then you're trying to model it using first principle based physics, you have to make some approximations. So for example, in this case of the picture that you see here, in which you see a environmental system with weather driving it, and then the system has soil, and then when the water falls, depending upon the characteristics of the soil, the water would get absorbed in different layers of the soil. And that exactly how that water gets absorbed in different layers of soil and how it moves through the system determines the hydrology, determines the ability of the agricultural systems to make effective use of that nutrient. And all of this involves being able to model this environment. And as you can see in the upper part of this picture, the soil actually is not a monolithic soil. It has different layers. And if you're trying to really build a really good model, you would like to model this. You would like to sort of represent different layers of this soil in some form in your physical model. Now, if you increase the number of layers, the model becomes potentially more accurate because it's taking greater information into account. But as you increase the number of layers, the computation becomes much more expensive. And of course, this is just one example, but you could be talking about modeling multiple phenomena, multiple processes. And if you're trying to model the phenomena, the processes that are changing very fast, rather very rapidly in space and time, then you have to sort of increase the amount of computation to be able to account for that. So basically, either because of the computation or scalar capacity trade-off, you have to often make approximations. So in many hydrological models, for example, rather than having many layers, they might just have one layer or may have small number of layers. That's one problem. That is, you may have physics that is missing. It's incomplete either because you couldn't find enough computation to handle it, or because you just did not have that information. So it basically results in inherent model bias, which means no matter how good a job you do to build that scientific model, that model will always be limited because it's not representing the phenomena at the right level of detail. The second problem is that even if you try to represent the phenomena at increasing level of details, which of course happens as you get more and more computing power, then as a result, you have to deal with more and more parameters. Because once you create 10 different layers of the soil, then you have to figure out what are the properties of that soil at each of those layers. And for every parameter that you are creating at a very different layer, you need to find the value of those parameters. And then that requires a lot of data to be able to figure out what those parameters should be. So in the environmental community, especially in hydrology, that problem is called equifinality. That is, if you have too many parameters and too little data, then multiple representations of the physical system that are completely different from each other might look the same, and which is, of course, not quite good. So these are the two big issues with process-based model. That is, if either you simplify the physics, in which case you have inherent biases, or if you have too many parameters, then you have equifinality. You will never have the kind of data that you need to parameterize them, except in very, very small cases. And the third limitation of process-based model, which actually is most serious and which is where the machine learning paradigm offers a lot of opportunity, is the following. That is, in the case of process models, if you build a model that has a number of parameters, and most models will have a large number of parameters, then to find the values of those parameters, you will need certain observations. And observations that you, for example, for a farm, if you are trying to figure out how the different management practices impact the greenhouse gas emission, you will need to know what kind of soil it has at different level of details, what may be the groundwater, what may be the groundwater flow, what may be the vegetation nearby. There are a whole bunch of things that you would sort of need to know, and before you can sort of study the impact of different management practices on greenhouse gas emission. But as you move from one farm to the other, then you would need, every farm would need a lot of observations to be able to find the values of those unknown parameters for the physical model to work. And those models are so plentiful, oftentimes these models can provide you some information, but they can never provide the information at the level of detail that you really need, for example, for introducing carbon markets. And if you go from a farm that you have instrumented very heavily, for which you have calibrated your model extremely well, and if you go from that location to a different location, to a different farm, then you need to start this process all over again. That means you need to find new sort of observations to be able to work there. So the traditional process-based models are very good in using physics, and of course they're limited by the ability to bring in all of the physics, but they're very inefficient in making use of the observations. So that is a calibration of a process model on a highly observed system, on entity, can help only for that entity. It helps modeling only for that entity. It does not help improve performance on a less observed or unobserved entity. Now, this is where the machine learning methodology, even in this original form that's developed in the last 5 to 10 years, comes very handy, in the sense that machine learning models are actually meant to be able to solve this kind of problem much more effectively. Of course, the traditional machine learning models have the issue that they don't work with sparse observations, they don't generalize to unseen scenarios, and they produce physically inconsistent results. So these are all the issues that this machine learning methodology that's guided by scientific knowledge is supposed to address. And then using some of the other advances in machine learning, we're able to bring this KGML paradigm to also basically leverage information from highly observed entities to provide high quality prediction in unobserved or sparsely observed entities. So this is collectively these are the advances that we are able to make at the interface of science and machine learning to be able to address some of these huge problems. And in the rest of this talk, I'm just going to give you snippets of some of these successes that have been able to do, and how all of these successes are leading towards the objective of the I-climate. So here I'm showing you some of the earliest work we did in collaboration with the USGS in our ability to model lakes, the temperature dynamics of lakes, using a methodology which combines both scientific knowledge and machine learning. So what you're seeing in the slide is a lake, which happens to be Lake Mendota, for which the modeling was done. It's supposed to be a very highly observed lake, probably the most observed lake in the world, and because the USGS has one of their offices located right there at that lake. And they use GLM is a physical model that they use for modeling this lake. And what you're seeing on this graphic here is that as you add more and more observations, which is shown on the x dimension, on the horizontal dimension, as you have the number of training observations ranging from a small number like 2 to 10 to a few hundred, the performance of this model improves. On the vertical dimension, you see as you go up, your error decreases, which means the performance improves. And this, you're able to model this lake to a reasonable level of performance because you have a lot of data. But the amount of data that we have for this lake is unique. It's the, as I mentioned, it's the most observed lake in the world. For the rest of, there are about 180,000 lakes in the United States alone, and for that, the amount of data at the level of this lake is only available for only about half a dozen such lakes. For about 10,000 lakes, we have some amount of data, and for most of the remaining 165, 170,000 lakes, there is no data at all available. Which means if you're trying to figure out what's happening to those lakes, you're sort of driving blind. Okay? Now, if I have a machine learning methodology, the traditional machine learning methodology, the standard method that you would use for modeling languages that out of the box, it actually can do extremely well if you give it a lot of data. As you can see here, the orange curve for a very large amount of data is exceeding the performance of a black box of a physical model. Okay? That means if you have a lot of data, you don't need science. You could just work with the observation itself, right? But of course, as I said, you don't have this kind of data for most lakes in the world. But if you have this methodology that we have developed, process-guided deep learning method, the knowledge-guided machine learning, you can see that it can work with extremely small amount of observations and do better than both of these schemes. And of course, as you get more and more data, then eventually everybody gets pretty much the same. But the basic thing is that for most of the lakes in the world, you have very small amount of data, or sometimes even no data, and you can still do extremely well. For them, you can see the purple performance curve is higher than all of the other ones, and pretty decent even at the low end of this thing. So this tells you that yes, combining knowledge and machine learning can deal with the problem of sparse data sets. But this next slide says actually something even more important. That is, it could also help you make predictions in scenarios that have never been seen. So here is the same problem being shown, and then you have two different graphics here. On the left side, what you see here is that your training and test scenarios happen to be similar in the sense there's multiple decades of data, and a decade of data was used to build the model. Another decade was used to test the model. That means all of the, you can sort of say that test data is representative of the training data. And you can see here from these different numbers here, for a large amount of data, in each case you have about 500 days worth of data. You can see here that the process models does provide you error of 1.5. Machine learning provides you error which is lower than 1.5, and the knowledge-guided machine learning method provides you even smaller error, which is consistent with what we saw on the previous chart. But on the right side, what you're seeing here is something more dramatic. In the right side, all of these three paradigms were shown only 3 of the seasons in the year, and the summer season was kept out for all 3 of them. That is, the idea was that all of them are able to see data only from the 3 seasons, and let us see whether they can make predictions in the summertime, which they have never seen before. And as you can see here on the right side, once you take the summer out, even the physical model performance goes down, because for the calibration, it doesn't have access to the summer data, which means it doesn't know what the summer looks like. So some of the model parameters values become incorrect. The pure machine learning algorithm, which is in the middle, the orange one, becomes extremely bad because machine learning has no clue as to what happens in summer in a place like Midwest relative to winter and fall and spring. But if you look at this knowledge-guided machine learning algorithm, it degrades very gracefully and is significantly better than both of the other schemes. This was perhaps the first demonstration of the ability of a machine learning algorithm guided by scientific knowledge to generalize to scenarios that are out of sample, and it shows the power. Now, since then, of course, this methodology has been used by USGS in many scenarios, and to show that it can provide information predictions on very large scale, and I'll come to those results in a minute. And then this slide is simply saying, it's a very busy slide, but it's supposed to sort of show that if you are trying to measure the energy and how it's coming into the lake system from the sun, what portion of it is being reflected back into the air, and difference of that should be warming or cooling the lake. And if you look at all of these components in a physical system, of course, you will see the energy to be conserved. Energy is supposed to be conserved. And if you try to look at how much, if you do this computation for these physical system, GLM, physical process model, the KGML model, which is in the middle, and then the plain machine learning model that's on the top, and you can sort of see that yes, the KGML model actually is extremely good in terms of being able to conserve energy. Now, in the last piece of the talk, I'm going to spend a little bit more time on one aspect that I talked about earlier, which is the unique ability of machine learning to transfer information from more efficient transformation more efficiently than process-based model across both space and time. And as I mentioned earlier, this is one of the biggest issue with process-guided model or the traditional physics-based model. And machine learning is very powerful here, and this is the capability of machine learning that we bring into KGML to bring a lot of power to modeling this scientific system. And to explain that, I like to sort of explain this figure a little bit more. So what you're seeing in this figure is a matrix, and the rows of this matrix correspond to entities. And entities in our case could be a farm, could be a river catchment, could be a region, the ecoregion, and the horizontal dimension happens to be time steps. It could be days, could be weeks, could be years. And the green area is sort of what you are sort of saying, that we have certain entities, like certain farms or certain ecoregions, for which we have data over a period of time. It could be for a decade, could be for a couple of years. And that data is the one that one could use for training machine learning model, or that data could also be used for parameterizing the process-guided model. So green area is the one that's used for building a model. And of course, in this case, we'll be building a machine learning model. And once you build the model on the green, on the top left corner, then for each of the entities, you could extrapolate in time and do a better job of making predictions into the future. So in a typical process-guided scenario, what you would do is you will take an entity, you will get some data to calibrate the parameters, and then you will use this calibration to go into the future to make prediction. So this is what is often meant by being able to do prediction using physics-based model in well-observed systems. So if you're staying with these green entities on this curve, process model would basically be calibrated for each entity separately and extrapolate. Machine learning model has the ability to use data collectively from all of the entities together to build a model and then extrapolate it into the future. And because machine learning model is able to use data collectively, it can leverage information across all of those entities, all of the green entities, via frameworks such as multitask learning. And they can actually be a lot more powerful than the traditional process-guided model, because they're using observation from each entity separately, whereas the machine learning can use data from all of the entities collectively. And already for the scenario in which you're extrapolating in time, it has been shown for a number of environmental applications that this methodology, machine learning-based methodology, actually provides much better performance than physics-based models that are individually calibrated for each entity. Right? So this is a place one could say that machine learning models have already shown a dramatic improvement in performance. And again, this has been shown both by our research group and also for many other research groups around the world. And all of that happened in the last 5 years. So this is a very recent research idea. Now, the biggest challenge is in going from the entities for which you do have observations, like the green entities, and you want to go to entities that are outside of these entities that you use for training. So basically, you're talking about extrapolating in space, okay? Which is the lower part of this figure. Or you're extrapolating in both space and time. That is, you're going to new entities and entirely new regions. Now, in both of these cases, the traditional process-based model actually don't do very well. It's a very difficult problem. It's called the problem of regionalization. That is, you try to calibrate a model in a new place by trying to understand exactly how the parameter of this model would be in a similar entity for which you have the observation. And it's a problem that's imperfect, and it doesn't do very well. But in the case of machine learning, there is a possibility of transferring knowledge across these two different sets. That is, across going from highly observed entities to low observed entities, using frameworks that the community has built. And again, for in a machine learning community, these are called zero-shot learning, in which you could just go point. You can go to another entity without any observation, but then you need some sort of a surrogate characteristics to be able to transfer information. Or if you don't have surrogate characteristics, and if you have sparse observations, very few observations, you can still make the transfer. So basically, there are methodologies that have been developed to go out of sample and extrapolate in both space and time, which is a very difficult problem. And that is the area where the KGML really shines. That is, using the machine learning power combined with the scientific knowledge, this extrapolation becomes much better quality and much more powerful. And I'll just give you a couple of examples here. And this is, I mentioned to you, the ability to model lakes around the US. The USGS is responsible for it. And I mentioned to you that there are 185,000 lakes, and the date observations are available only for about a little over 10,000 of these lakes. Now, the question is what's happening to the remaining lakes, and you have no understanding. And this methodology that I just mentioned to you, this ability to go out of sample, was used for the first time to create predictions of temperature variations for all of the lakes in the entire country, and that was enabled only because of the KGML methodology, combination of machine learning and scientific knowledge, and it became a data set available to the scientific community for the first time. There's another one that's sort of closer to the very direct goal of the AI climate, is being able to monitor global carbon fluxes. At the end of the day, we are trying to figure out how much carbon is being emitted by different components of the ecosystem, including agriculture and forestry, and the scientific community has built flux towers at different places in the world. And wherever you have a flux tower, you have actually very good observations of what the carbon emissions are. But you cannot populate the entire globe using these flux towers. But the regions that have flux towers actually create entities that are highly observed. And this methodology that I told you about, that is being able to go from highly observed entities to less observed entities, basically comes in very handy in taking this models that are trained using highly observed areas and then taking them to areas which are sparsely observed or unobserved. And in this case, we are taking them to unobserved entities where we have a little bit of observations. And again, this slide actually is telling us two things. That is, one, the machine learning can do a better job. And the second thing is that the KGML methodology, that when you bring in the knowledge guidance into the machine learning, it can do a dramatically better job. And basically the results on the right side of the slide sort of show you that if you bring in the machine learning methodology combined with knowledge guidance, which is what we call TAMRL in this particular case, you can produce much better results using far less data for the global carbon fluxes on a global scale. This next slide is sort of illustrating the ability of these KGML models to be able to represent different phenomena that are happening at spatial and temporal scale. And again, this just to summarize what this slide is sort of showing is that you see the stars values are the actual predictions of river flow stage in an area which is managed by NOAA in one of his weather centers in Minneapolis, and that's the true observations. And you're trying to make predictions for these observations 7 days in advance. So you're looking at you're standing at time 0, which is today, and you're trying to make predictions going 7 days forward every 6 hours. And of course, since you're looking at it after the events have happened, we can see the stars are telling you exactly what happened. And then all of these different curves are sort of telling you what you could have done using different methodologies. And the red and the yellow curves are showing you what you can do using traditional machine learning methodology. And what you can do using traditional machine learning methodology is very similar in the same ballpark as what you could do using the process-guided methodology, the traditional scientific methodology. But when you combine them together, you get the blue curve, which sort of gives you the ability to make predictions even multiple days in advance and rather accurately. And the last one, I just want to sort of remind people as to how all of these things are coming together in the context of AI climate, whose one of the major research themes, the first research theme in the project, is being able to quantify greenhouse gases and carbon sequestration capability of agriculture. And biggest knowledge gap here that exists is not having a lot of data and inability to make predictions in scenarios for which data sets are not available. And the approaches that we are developing here are our ability to model complex physical processes that could be evolving, interacting at different scales, being able to do the transfer from highly observed regions to sparsely observed regions or unobserved regions using scientific knowledge, and being able to assimilate additional sources of data that are available in, via remote sensing, and sort of being able to somehow represent the impact of crops, environment, management practices on greenhouse gas emission. And again, the fact that we have the chance to succeed in this area is sort of shown by some of the examples that I've shown you earlier. That is, we have been able to model the physical process at different scales in hydrology. We are able to already improve the accuracy for greenhouse gas emission in agriculture using some of these methodology, and then we can scale up these models to broad regions. These are some of the other examples that that sort of show the application of KGML methodology, ranging from being able to model the dynamics of the ocean, which you see on the top left, to top right, which is being able to figure out what crops are growing at what locations, in this particular case showing two different photographs of two different representation of what crops are growing in a region in California, and of the two figures that are right next to each other. The left one is coming in from the crop data layer of USDA, which is very fragmented and visibly incorrect. And on the right side, you're seeing a new crop map being developed using this methodology. And again, being able to find out exactly what crops are growing is one of the components that sort of goes into the KGML framework that sort of leads to greenhouse gas emission modeling. So in conclusion, as you can see, big data and machine learning offer tremendous opportunity to increase our understanding of Earth's climate and environment. And this paradigm of machine learning combined with scientific knowledge is particularly relevant for AI climate, given its ability to bring in scientific knowledge into machine learning framework to address the limitations of traditional machine learning as well as the traditional scientific models. And the challenges that are unique to these environmental problems actually require us to advance the frontiers of machine learning in the sense that how do you build new approaches that can guide the process of knowledge discovery in scientific applications. And this methodology of knowledge-guided machine learning is applicable across a very diverse range of applications. Ecosystem management, as we just talked about, but even domains as different as epidemiology, geospatial intelligence, even understanding the brain and understanding the workings, inner workings of the brain. Thank you.